straightforward. You have a stable baseline, energy dissipation too. Stable baseline. Yeah. Yeah. What is the? They have different color. Very hard to see. Do you have any red one?
We have black one.
Black one. Can I have it? So in the case, the surface, you have sensor surface is nothing but you have just buffer in here. Okay. And then now we introduce the Basco. Basco start observing on the surface, basically impacting, another one intact, and then now the frequency changes. Frequency goes down, that means it's increasing the mass. So frequency goes down up to saturating the Basco, impacting on the surface, like as you see the example in here, as you see the drawing there, and frequency continue going down, and then after they saturating, no more Basco can find the surface position, so that's why they stabilize. So this is the frequencies. And what happened to the energy dissipation? Take a look at this Basco. This is the shearing force. They shearing continuously due to the electricity pulse applying onto the quartz crystal. What happened to this very soft balloon kind of Basco? They moving randomly. They create the energies and then dissipating to the surface. So they create energy dissipating to the surface. That's why they increasing the energy dissipation. Okay, so this is a very straightforward case of the oxide gold surface. So you guys now confused about what happened if we change the surface. This is gold case. Now we change it to the silicon oxide case. Assume that this is a silicon oxide. So what do you have silicon? What is the property of the silicon oxide? We learned from the class. What is the silicon oxide surface property? Silicon oxide is a hydro. Huh? Oh, silicon oxide is hydrophobic. Right? Are you sure? Since when? Is this silicon oxide is hydrophobic? Silicon oxide have an oxide layer with a hydrophilic group, right? And which is highly hydrophilic rather than hydrophobic, right? It's the opposite, which is good. At least you know half. At least you know hydrophobic. So when you have an exam, you can either say hydrophilic or hydrophobic, and then you got 50. So what happening here, same fashion, I'm start adding Basco. Same thing. This is called silicon oxide, I'm doing same thing, start adding Basco. Basco observing on the surface up to the critical point. So this is the critical density point. And what happened in here, in this particular case, the question is why vesicle intact on the surface not rupture, because they don't have a sufficient interaction with the gold and with the Basco. And then they have a sufficient interaction, that's why the Basco observing on the surface, but they don't have a sufficient interaction, interaction between the Basco substrate, so it cannot be ruptured. But however, in this particular case, you have a sufficient interaction with the Basco, but very strong hydrophilic interaction with your phosphate heavy group. You learn from the lipid phosphate heavy group with a hydrophilic substrate. So what happens is that they start to rupture. This big Basco have fused together, and then they also have a very strong interaction with the substrate. They start to rupture on the surface. If Basco rupture on the surface, hydrophilic surface, what happens? They start to create liquid bilayer. That's what is showing in this drawing. When they start to make liquid bilayer, what happens is frequency changes. They're losing mass, right, in this particular case. Instead of adding mass, they're losing mass, that means increases the frequency up to a certain point. What is this certain point? Is defined as 26 Hertz. What is the 1 hertz meaning? 1 hertz meaning is basically 17.7 nanogram. Take a look at the unit very carefully. This is not just mass. Area density mass. Nanogram centimeter square per second. Okay? So this is area density. This is mass. So this 1 hertz corresponding to the mass changes of 17.7 nanogram. So what happened to the energy dissipation? You do the same thing up to a certain point. But what happened? Why suddenly energy go back to the zero? So as I mentioned, you have a substrate is sheared by the electric pulse applied. When you have a vesicle, the vesicle moving different direction, random direction. But when you have a straight, very thin 5 nanometer lipid bilayer coating on the surface, like this, your iPad coating on your surface. When the substrate moves, this surface moves together along the same direction. Because it's very weak, it's acting as a fillet. So that's why your energy go down, your dissipation disappears. There is no more energy dissipating to the substrate from the lipid bilayer. That's why you got this shape. The question we have in here, basically, the group practice we have in here, basically, if you adding, instead of this single vesicle, if you adding this multilamellar vesicle, what are you expecting your signal changes? What is your gas? What's going to happen? Because in this particular case, we are not talking about single vesicle layer. We are talking about multilamellar lipid vesicle layers. What's going to happen? That was the question in here. Okay. Anyone have any answer based on this free container energy dissipation changes? Any have any guess what happens on the silicon oxide surface if you're using the multilamellar vesicle? Any clue? Anyone want to do the practice? This is what you want to have? Frequency energy changes, you guys done? Who want to try out this one? Anyone? You want to try? Huh? No, you can try, it's fine. Your data looks fine. Try it. It's okay. We can